Mainstream psychology often defines trust as a static belief, as an expectation, or a fixed personality trait. In this view, you either possess confidence in someone's dependability or you do not. But this definition ignores a core mechanical paradox. If trust is a fixed trait, it should remain constant. Yet between the exact same individuals, interacting under identical external conditions, trust fluctuates wildly from one day to the next. This formula illustrates that trust is an actively updating, context-dependent state. The output, trust, is continuously recalculated based on an array of variables: historical interaction, environmental context, internal physiological state, future expectation, and the time elapsed since the last reinforcement. A change in any one of these variables forces the entire system to recalibrate. An individual experiencing high physiological stress will generate a different trust calculation than they would in a rested state, even if the other person's behavior remains identical. Modeling trust as a static trait fails to account for this systemic volatility. It offers no mechanical explanation for why stable relationships oscillate or why sudden betrayals occur. The human brain is a prediction engine, and running that engine requires a disproportionate amount of the body's metabolic resources. Evaluating every social interaction from a zero baseline is computationally impossible. Trust solves this resource problem. It operates as a routing protocol, a priority pass designed specifically to conserve cognitive energy. When trust is established, incoming information is accepted through a low-resistance, low-cost neural pathway. When distrust is activated, the brain routes the information into high-friction processing to verify data and monitor for threats. To understand exactly how the brain regulates this cognitive load, we have to look at the physical neuroanatomy of trust and map it onto the Brain Kinematics Model, a framework that measures the physical stability of neural coupling. Trust is a metabolic survival strategy. The brain uses it to avoid computational overload. The routing protocol operates through a dual-gate architecture, splitting incoming data into fast affective filtering and slower cognitive processing. This cross-section highlights the first gate, the affective system. Here, the amygdala and the striatum evaluate incoming signals for threats and rewards. Data is sorted instantly, operating entirely below the threshold of conscious thought. Because this affective gate must prioritize speed, it relies heavily on prior attachment templates and emotional memory. It makes rapid, low-precision judgments under strict uncertainty. The second gate is the cognitive system, located in the prefrontal cortex. This system slowly re-evaluates the initial signals, factoring in the target's competence, historical integrity, and the broader environmental context. The metabolic trade-off between these two gates is steep. The cognitive gate provides high precision, but it requires a massive expenditure of energy. The affective gate is highly efficient, but prone to distortion. The brain actively regulates this balance using neuropeptides. Oxytocin pathways, for example, dampen the amygdala's threat response, forcing the gate open to promote social risk-taking and bonding in specific contexts. Trust emerges from the constant tension and interaction between these two distinct neural networks. If the mechanism relies on the internal state of these networks, we have to address how trust changes when the external evidence, the actual behavior of the other person, remains the same. This visualization of the internal modulation equation demonstrates the mechanics of that shift. The X variable represents the objective external signals. They are locked. The W variable represents the internal weights assigned by the brain. When the internal weights fluctuate, the final trust value changes without a single new piece of external evidence. Because emotional baselines act as field conditions, they determine exactly how heavy or light the interpretive weights will be for any incoming signal. A state of affection operates as a cohesive field. It increases the system's tolerance threshold. If a signal deviates, a delayed response, or a minor error, the system absorbs the friction and maintains the trust pathway. Anger and resentment create a fragmented field. The tolerance threshold drops. Micro mismatches and ambiguities are assigned heavy, negative weights, causing the trust calculation to plummet. The baseline can shift from factors that have nothing to do with the relationship. Fatigue or acute stress increases the amygdala's baseline sensitivity. A previously neutral signal is now routed through a high-threat suspicion attractor. The level of trust you place in a system or a person is largely a measurement of your own internal physiological stability. To quantify these shifts, we translate neural activity into the Brain Kinematics Model, which maps the physics of how separate entities interact over time. This diagram maps two network nodes, the self and the other. Under the Brain Kinematics Model, trust is defined as the physical stability of the strain flow between these representations. When the coupling is stable, interactions pass through with low resistance flow. If the timing or intent of the two nodes misaligns, it creates a phase mismatch. This introduces turbulence and friction directly into the coupling pathway. Indirect signals, like secondhand narratives and rumors, bypass the direct feedback loop between the nodes. Without a direct mechanism to correct the data, the pathway warps and distorts. When an individual's internal self-image contradicts the identity assigned to them by the external environment, a narrative gap opens. This gap continuously generates friction, destabilizing the entire system. Trust and control share an inverse relationship. Optimal trust relies on balanced strain flow with minimal correction force, whereas low trust demands high-cost monitoring. Trust breaks down when the coupling pathway accumulates too much uncorrected strain, disrupting the energy-saving flow. The brain anticipates these breakdowns. It regularly runs offline simulations, experienced consciously as dreams, to test the limits of the coupling pathways and calibrate social strategies. A common simulation parameter tests a specific vulnerability, a scenario where an authority figure applies judgment based entirely on a second-hand report, refusing direct interaction. The simulation is testing the systemic danger of a second-hand identity. When an external force dictates the narrative, the direct strain correction loop is severed. The individual loses the ability to correct the distortion. Within these simulations, the brain isolates variables to test for risk. Empathy is one of the most volatile variables in the trust equation. Computationally, empathy functions as an open boundary condition. It lowers the separation between the self and the other node to allow maximum data transfer. The paradox of empathy becomes clear in the mechanics. Lowering the boundary increases the potential for a highly efficient, strong trust coupling, but it simultaneously leaves the internal system exposed to narrative distortion by external forces. Empathy deployed without strict narrative boundary control results in severe identity instability. The open boundary becomes a liability. When the coupling pathway finally fails, it produces the psychological illusion of a sudden betrayal. But mechanically, trust never collapses without a prior history of strain. This graph traces trust failure through a 5-stage trajectory. In formation and reinforcement, behavioral signals align into a low-energy coupling. During the distortion phase, microstrains accumulate. Inconsistencies are absorbed by the system's tolerance threshold. Because the structure holds, the cognitive gate ignores mounting friction. Then comes the threshold crossing. The system absorbs one final, microscopic strain. The tolerance limit breaches, forcing a rapid, non-linear collapse of the trust pathway. Sudden betrayals are the visible result of long-ignored, accumulated microstrains finally crossing the tolerance threshold. Analyzing trust requires multiple lenses. Psychology identifies the human vulnerability. Neuroscience maps the neural circuitry required to evaluate risk. The Brain Kinematics Model explains the mechanical dynamics of the system. Translating this unified theory into physical architecture yields rules for designing resilient organizations and managing teams. Rule 1. Systems must engineer direct, rapid feedback loops. Without a mechanism to immediately resolve phase mismatches, invisible strain will accumulate until the coupling fractures. Rule 2. Organizations must reduce reliance on indirect narratives. Secondhand reports and rumors bypass the correction loop, distorting the node-to-node coupling. Rule 3. Individuals must map their own physiological baselines. Before reevaluating external signals, you must account for the temporary effects of stress and fatigue on your amygdala's threat sensitivity. Trust is an active, energy-saving dynamic system. Mastering its kinematics allows us to build, regulate,